Today we're going to be talking about vector products. They're actually, we saw in the last video how to add two vectors. As long as they were the same dimension, we can add two vectors or subtract them. And of course that was pretty easy to do. Component form, a little harder to do if they were in magnitude and direction, or so-called polar form. Now when we get to multiplying vectors, there actually have three different kinds of vector products. The first one we're going to do is called scalar multiplication. And scalar multiplication is where we take a scalar times a vector and the answer will be a vector. Another type of multiplication we have is called a dot product. In a dot product we have a vector dot another vector and we get a scalar. And the final product is a cross product. This will only be defined for three-dimensional vectors, but we have a 3D vector cross a 3D vector, and that becomes a 3D vector. Notice that we're using the dot version of our multiplication symbol for the dot product, where we get a scalar, and we're using the X version or cross version of our multiplication symbol when we have a vector answer for our product, a cross product. This video is going to focus on the scalar multiplication, and we'll follow up with multiplications for the videos for the other two multiplications. Now each of these has an interesting geometric meaning as well as an algebraic definition. So let's look at the scalar multiplication as we click on this. So we're going to define algebraically scalar multiplication. We can do it for any dimensional vectors, for any dimension n, by multiplying the scalar by each component to get the components of the product. So, for example, or by definition, if you have a scalar alpha and a vector v, which has components v1, v2, v3, and so forth up to vn, then alpha times v is alpha times v1, v2, v3, vn. And so that is alpha v1, comma, alpha v2, comma, alpha v3, comma, da da da, up to alpha v sub n. So, for example, let's look at this example here, this first example. Let's just do it here. And we have alpha is 2, u sub x is 1, u sub y is negative 2. So x is 1, y is negative 2. X component is 1, y is negative 2. So vector u is 1, 2, 1, negative 2. And alpha is 2. So we just take alpha times u, and that's 2 times 1, negative 2, which is 2 times 1 is 2 for the x component, and 2 times negative 2 is negative 4 for the y component. Okay, well, what does that do for us in terms of the vector? Well, if you notice, it basically doesn't do anything to the direction, but look at the length of this thing. The length of the vector is now twice as long as the vector was to begin with. Now we can prove that, as you see down here in our geometric interpretation. So if we do the norm of alpha times v, it's the norm of this, right? And so that means we square each one of the components, add them up, and square root. Well, when we square this, we're squaring each part, so each one of these has an alpha square, then a v1 square, alpha 2, alpha square, v2 square, and so forth. They all have an alpha square, so we can factor that out using the distributive property. And then we can break this into two square roots. Okay. And the square root there of a square is the absolute value of a, or alpha is the absolute value of alpha, and then this part here is exactly the norm or magnitude of v. And so we see that we get the magnitude of alpha times v, a vector v, is the size of alpha, the absolute value of alpha, times the size or norm or magnitude of the original vector v. Now, it turns out that the alpha is not going to affect the angle any, Okay, if we go back and do the angle here, if you just think in 2 dimensions, we can see, let's see how we can do this in 2 dimensions. So if we have if you take v sub y come on, and then we do over v sub x. Okay, we take that and we want to multiply that by alpha. So we multiply the x and y components by alpha. That reduces to the same thing. Because the alphas cancel. And so that's the tangent of the theta for the vector v. Okay. Whereas the on the other hand, this is the tangent of the vector alpha times v. Okay, so we see that the two tangents, they have the same tangent. So, another thing to notice is that the vector -1 times v points in exactly the opposite direction as v, so the arrow is reversed. So, for example, if you just think of the vector that goes from 1, 1 versus the one that goes -1, -1, they're exactly opposite directions of each other. They have the same tangent, but they're opposite directions. So, it turns out that if you multiply, if the alpha is a positive scalar, then the angle doesn't change at all, as we see here in these pictures. These are parallel, or if we start them at the same point, you can definitely see that they're going in the same direction. Over here you can see they're parallel, and the arrows are on this sort of the same end. Okay, but if I were to make this a negative scalar, let's say put a -2 here. Now notice that the arrows on the opposite end, they're still parallel, still twice as long, but it's going the opposite direction. Okay, and so we have, when we multiply by a negative scalar, we reverse the direction. Okay, and so you can see there what happens in the component form. Now, let's look at an example. Let me change that back to positive. Okay, let's hide that example. Let's look at an example in magnitude and direction form. So, so we saw in the component form one over here, we just multiplied each component by the alpha. What do we do if we've got it in magnitude and direction form like this? Well, here I've chosen a negative number for beta, and a vector v is 3 as the magnitude, and the theta, I've given it in degrees here, is the 20 degrees. Okay. Now, so that's the purple vector v. What's the vector beta times v, which is the red vector? Well, its norm will be just the absolute value of -2 times 3, so it's 6. So this one's going to be 6. Twice as long. Okay? But it's going to be in the opposite direction. So the theta is the same. Theta doesn't change if beta is positive. If beta is negative, you add pi radians, or 180 degrees. And so in this case, it's 200 degrees is the angle here for this one, so that it's pointing in exactly the opposite direction. As usual, these are dynamic. You can fill in the three measurements in the blanks, and it will work out the examples here. So that shows you what happens with scalar multiplication. Review: in component form, you just multiply all the components by the alpha. In magnitude and direction form, you just multiply the magnitude by the absolute value of the scalar. The angle theta will stay the same when the scalar is a positive number, and if the scalar is a negative number, then the angle will be exactly the opposite direction. The arrow will be reversed, still be parallel but reversed, which is you've added 180 degrees or pi radians to your original angle to get the new angle. One final word: if you multiply a vector by the zero scalar, you get the zero vector, which has all components 0. Okay, and this type of product, even though we're probably just going to do it in 2 dimensions or maybe 3 dimensions, it still works. You can generalize this concept very nicely to 4, 5, 6, 16 dimensions. It doesn't matter. So that is the scalar product, a scalar times a vector, giving you a new vector. So basically, multiplying by scalar is going to stretch it or compress it or possibly flip it over as well to the opposite direction.